All right, let's go ahead and get started. Hello, my name is Alex Ingerman. I'm a product manager on Amazon Machine Learning, and I'm so glad to see so many of you here in the room. I'm guessing most of you have heard about Amazon Machine Learning from Andy Jassy's keynote earlier today. If not, I'm going to tell you quite a bit more about it. So welcome aboard. I have an hour of your time, and I'm going to try to make best use of your time. I want to start off by telling you a little about machine learning and where it fits in the overall data ecosystem, and how this machine learning technology can be used to build what we call smart applications. I'll give some examples of smart applications, and I'll give one counterexample, or a counter pattern of how to not build a smart application. Then I'll switch over and I'll talk about the service. I'll tell you a bit about the features and benefits of Amazon Machine Learning. And because this is an advanced session, I want to make sure that you walk out of this room knowing how to use the product. I will walk you through an end-to-end process of building and deploying and using a machine learning model using Amazon Machine Learning. And then I'll open up the floor to Q&A. So let's get started by talking about data and the way data has become really a part of the fabric of the applications. What we know, what we have seen internally at Amazon, what our customers have told us, is that working with data has become a new competency for developers. In addition to doing front-end and UX work, in addition to doing mobile work, in addition to doing back-end development, all developers are now doing something with data. And in turn, data has turned the development of these applications on its head. Applications now log, instrument, and store a tremendous amount of data, and so developers are picking up the skills to analyze this data, to derive some value from it, and to build useful applications on top of the data that their application generates. So what we know, what we have seen from our customers is three main types of data-driven development. And the first and most common is retrospective analysis and reporting. In this kind of applications or in this kind of data usage, existing applications generate large volumes of data that customers store, for example, in S3 or in Amazon Redshift, our petabyte scale data warehouse, or in RDS. They process this data. If the data is in S3, they might process it with EMR using tools like Hive or Pig. If the data is in Redshift, they might run analytics query against it. The goal is always the same, to find some insight, find something about these customers' business that the data can tell them, and then use that insight to improve the business. A very common application is instrumenting how long your customers spend in different parts of your application and how successful are they, and then looking at the reports and finding problem spots, being able to improve the application based on what you find. The second type of data-driven development that is becoming more and more common is the here and now, being able to look at the data as it comes in and do something with it. Perhaps just build a dashboard so the state of the business can be seen exactly as it is today, not as it was yesterday or a week ago. Perhaps using products like AWS Lambda to respond to events as they come in. This is really powerful because it allows immediate reaction to the conditions that your application and your businesses encounter. There is one more stage beyond the retroactive and beyond the here and now, and that's the prediction stage. Predictions enable developers to build applications that make a powerful, correct prediction about the future and then do something with that prediction. And so this brings us to machine learning. Machine learning has many definitions. One of the broadest, and I find most useful, is to think of machine learning as the technologies that can look through the data and find patterns. And then once these patterns are found, it can act on them by looking at a new data record and making a prediction that leverages the patterns that have been found in the past data. So there is a very simple equation here. Take your data, add machine learning technology, and smart applications become possible. What are some smart applications? Well, I'll run through a few examples, and you may have seen these already in the keynote. I'll go a little deeper. But one very common example of smart application is, based on what we know about a user, will they use your product? How long will they use? Will they upgrade out of free tier? Should they be contacted with a business development opportunity? that is a great example of leveraging what you know about your user to make a prediction and act on it. Another example is, based on what you know about an order, is this order fraudulent? Should this order be flagged for manual review? Should you contact the customer and confirm they placed the order? Should you cancel it directly? These are all choices that are available. And a third example is, based on what you know about a news article, what other articles are interesting to your audience or to a specific person? And that is just the tip of the iceberg. The list of machine learning applications out there is enormous. You have fraud detection of all forms, from transaction to spam emails to suspicious review, personalization, targeted marketing, content classification, churn prediction, customer support. It just goes on and on. It's really exciting. But the question is, why don't we have more smart applications? And I want to talk about it by first introducing a little bit of a counter pattern. Here's an example of an output of smart application. It's an email I might have received and says, "Dear Alex, this awesome quadcopter is on sale, just $49.99. And this happens to be really well targeted because I'm really into quadcopters. So the question is, how did this email come to be? Well, let's look at how one might approach the problem of we need to look at our customer database and find customers who would be most interested in this promotional offer of a quadcopter. We might start with a really simple SQL query. We might just look at all our customers who've placed an order in the last 30 days and say, well, that's good enough. They're active customers. Maybe they're interested. This works. It's not very well targeted, but it will give some results. We can make this query a little better. We can say, let's only look at customers who bought something in the toys category, so we don't lump in folks who buy books into this promotion. They're probably not interested. A little better. We can make it a lot more complex, certainly, by now joining in not only orders, but also products. We can ask, well, let's actually look at people who have bought something whose description has the word helicopter in it in the last 60 days, or made a big purchase, a purchase over $200 in the last 30 days. So you can see this query is now more complex. It has more numbers in it of unknown provenance. Somebody just made these numbers up. Is the targeting any better? I don't know. So because I don't know, let us forge forward and try to just make it better. Let's change our description. It's not just helicopter. It's just a string copter, because that includes copters, quadcopters as well. Let's go ahead and look further back in time. Let's look 120 days back. And maybe we're looking at big purchases made in the last 40 days instead of 30 days. And maybe $200 is not exactly the right threshold. Maybe we'll change it to $150. And maybe we'll change our copter order date to 90 days. And we can keep going like this forever, and it will never work. This is a path to failure, because you cannot put a query together with lots of magic numbers and discover a well-working, powerful targeting solution. And machine learning is a solution to this problem. Machine learning is what allows you to look at this data and find these patterns, find these business rules, and use them to target the promotion or to accomplish whatever it is that your smart application is doing. And so again, let's return to this question. Why aren't there more smart applications? What our customers tell us is that there are three main barriers. One is that machine learning expertise is rare. A second is that building and scaling machine learning technology is hard. And the third is that it's one thing to have a machine learning model. It's one thing to find these patterns. And it's a whole different thing to build an application that uses these models. That closing this gap is really difficult. And I want to drill down into this. Let's start by talking about the expertise. The truth is that to use machine learning today, you need experts. And there's just not enough experts available. Companies of all size, small and large, are feeling the squeeze that they cannot hire enough machine learning experts to work on all the predictive applications they want to undertake. Outsourcing is an option, but it's a very expensive option. Second barrier is the technology barrier. It takes significant time and engineering experience to build a machine learning technology, because there are so many choices available and there are so few mainstays. What we find at Amazon, what our customers tell us as well, is that no matter which technologies they start with, by the time they're done with their predictive application, they have build a hodgepodge of many different technologies. They use one technology to train the model, another technology to create the data workflows around it, a third technology to evaluate these models, a fourth technology to automate model retraining over time. And there are so many moving pieces there. All of these pieces are difficult to use and scale. They're not designed to be used together. And when you're done, when you've spent the time and money and effort to build this application, it ends up looking a lot like a custom solution. It's hard to take one application you've built and go and use it as a basis for the second application. And this brings us to operationalization, which is a connected problem. Working with machine learning is inevitably about data, about having a data workflows that can move data into the learning process to create machine learning models, that moves data into the prediction process to generate predictions. And building data workflows is hard and frankly unrewarding work. It's really difficult. To make a robust data workflow takes a lot of work and time. And what happens is custom platforms, custom APIs, custom everything, just to accomplish the data workflow, just to solve the data workflow problem. Beyond the building the data workflow to just create and build a machine learning system, what our customers tell us is that many of them end up reinventing the problem of machine learning model lifecycle from scratch every time. It is knowing when is my model accurate, when is the time to retrain the model. When I retrain the model, how do I know that I didn't introduce a data bugs that just took a model that used to work well and made it worthless? You have to build all this technology and all this wrapper code and all this glue to tie in disparate pieces of software to solve these. That's a lot of work. And so here's the end result. Machine learning projects today, they're really expensive, they're hard to get started with, and they're risky. You don't know if they're going to work or not. So what if there were a better way? You're in this room today because you've heard the rumors that there is a better way. And that is Amazon Machine Learning. Amazon Machine Learning is a new service that we have announced today to join the AWS service family. It is an easy-to-use managed machine learning service built for developers, not for machine learning experts. Also, we find that machine learning experts also use and like the service. It is robust. It is powerful because it's built on technology that's been battle-tested inside Amazon. Some of this underlying technology is used to generate tens of billions of predictions on a weekly basis. It easily connects and integrates with data you already store in the AWS cloud, removing these barriers of just connecting the dots from the data store to the machine learning technology to predictions. And finally, the production deployment takes one click. And depending on how you use your models, sometimes you don't even need that click. And I'll get to that in a little bit. All right, I want to talk about ease of use because that was incredibly important to us as we were building this service. What we have found is that building machine learning models really has these two stages. The first stage is experimentation. It is looking at the data you have and building models and trying out different data sources, different ways to represent the data, different ways to transform it, evaluating the results, rejecting the experiments that didn't work, iterating on the ones that did. And this kind of work is very well suited for an interactive workflow, just being able to work with data and with models directly. The second stage is being able to automate machine learning. Once we have models that work well, we need to put them on Rails. We need to be able to train them, to get predictions from them, together with the flow of the business applications that calls them. We may want to retrain them periodically with new data. And that second stage is all about having APIs and platforms that are as robust as your application. So what we did with Amazon Machine Learning is we've built both. Amazon Machine Learning is both a powerful service console to easily look at your data, inspect it, find issues, find errors, modifies and transforms the data, build models, deploy and manage these models. And it is also a full set of APIs to do all the same things but programmatically. And we have shipped Amazon Machine Learning support into all the common AWS SDKs, including Java, Python, .NET, JavaScript, Ruby. I have JavaScript there twice. I apologize for that. Lastly, I want to mention that Amazon Machine Learning prediction retrieval support is now built into the AWS Mobile SDK, making it effortless to write mobile applications that query for predictions and use them immediately. Next, I want to talk about technology. I already mentioned that Amazon Machine Learning is built on Amazon's battle-hardened internal systems. I want to make sure that when we talk about technology, we don't think of it as just the algorithms. There is more there. Amazon Machine Learning comes with smart data transformations. When you enter your data into Amazon Machine Learning, and I'll show you examples of how this flow works end-to-end, it is analyzed, and data transformations, or feature engineering and machine learning talk, are suggested automatically based on the data contents. There is a language built into the system to specify which transformations apply to which variables or which input attributes. You can take the suggestion directly, or you can edit it and modify it as needed. And there are industry best practices built into the systems throughout. These are things like ensuring that when a model's predictive quality is evaluated, it is evaluated on a fair holdout sample. It is surfacing up quality alerts when we detect, for example, that there are issues with input data or there are issues with models that's been built, and so on. And finally, Amazon Machine Learning is made to grow with your needs. It trains on up to 100 gigs of data. It can be used to generate billions of predictions, and you can retrieve these predictions either in large batches or in real time. And I'll get to prediction generation in just a little bit. It's important to note that we really wanted to eliminate this gap between data and models by making Amazon Machine Learning connect directly to the data that's already stored in the AWS cloud. With using Amazon Machine Learning console or APIs, you can use the data that already sits as CSV files in S3. You can connect to Amazon Redshift to execute a SQL query and grab the results, or to a MySQL database in RDS. The outputs of Amazon Machine Learning, the predictions, can be output into S3, from which they can be picked up by so many different technologies in the cloud and consumed. And the IAM is used for all the permission management to ensure that your application has the right security practices built in. And once you have a model, once you're ready to use this model to generate predictions, Amazon Machine Learning provides a fully managed end-to-end service for prediction generation. There is no hardware to manage. You don't need to know ahead of time how many predictions you'll need. The service is there to generate them for you, again, either in batches or in real time. It is effortless to deploy a model to production to make it available for prediction generation. It is easy to query a model to find out which settings it was trained with, what data transformations were applied, where did this data come from, what were the model hyperparameters. And this is powerful because it enables you to build model management systems that are appropriate for your application. You may, for example, build an application that trains a model with new data every week. And by querying an existing model, you can find out exactly which settings were used to train it so that your new model uses the exact same settings. And finally, there are CloudWatch metrics being emitted from model usage, so you can see the patterns of your prediction consumption, how many predictions are being generated. And let's talk about prices. One major barrier to entry for machine learning is just how expensive it is. We wanted to make it inexpensive, and we wanted to make sure that it is pay as you go. There are no upfront investments, no software, or no servers to buy. So the pricing model is simple. All tasks related to model training and evaluation, whether it's data analysis, whether it's the machine learning itself, whether it's evaluating a model, are charged at 42 cents per machine learning instance hour. And some of these operations are parallelized, so the total is based on the number of compute hours. They may and do, depending on the operation, finish ahead of the clock hours. Batch predictions are a simple 10 cents per thousand. And real-time predictions are also 10 cents per thousand. For real-time predictions, there is an additional small capacity reservation charge to ensure that the endpoint for generating real-time predictions is available for your application. And this charge only applies while you need the endpoint. When you don't need it, you destroy the endpoint, which you can do either through the console or through the API, and this charge stops. So let's talk about building smart applications. Let's actually look at what the software looks like and what you can do with it. There are 3 stages to building a smart application with Amazon machine learning. The first stage is building the machine learning model. The second stage is evaluating and optimizing this model. And the third stage is actually using the model to retrieve predictions. In the first stage, we go through a couple of steps. We first create a data source object that connects to your data and computes summary statistics on it and surfaces up this really cool interactive data exploration experience to allow you to look at your data and find errors in it. There is no machine learning technology that will work when your data is bad. And so we want to surface up this experience of finding data errors to confirm your assumptions and so on right in the beginning of the process. Once you're done with exploring and understanding your data, then comes the process of transforming it and building a model. So to create a data source object, what I'll do here is I'll show some of our UI, and then at the end, I'll also show you the programmatic way to accomplish the same task. We start off with a wizard in Amazon machine learning. Here we're asked a simple question: where is the data? We can connect to S3 or Redshift through this wizard. Once we fill in the location, the next step is schema, understanding the types of each attribute in the data. Now, the Amazon machine learning will actually go and retrieve the first few rows of the data and make a guess for schema for each data type. And in this step, you have the opportunity to confirm and correct that. Next, we select the target attribute. That is the things that we want to predict. Amazon machine learning uses a class of machine learning called supervised machine learning, which is just a way of saying that it works by being shown examples of the question you want to ask along with the correct answer. So for example, if we want to build a model that predicts whether a transaction is fraudulent or not, what you do is you enter in the transactions that your system has already seen, and you know whether they're fraudulent or not in retrospect because the bank has declined them. And so that is the target attribute. It is the attribute that holds this information about what is the true answer. Was this transaction fraudulent or not? So in this step, we simply select the attribute that contains that, and we move on in our way. And a data source then is created. Amazon machine learning reads your data, computes summary statistics on that data, and then surfaces them up to you. And before I move on to show you what the data exploration experience looks like, here is a very simple code snippet. I'm using our Python SDK here to create a new data source from S3. So as you can see, all I have to pass in is the location of my data, the location of the schema file, if I have that, and the flag to tell Amazon machine learning to compute the statistics. Once I have my data source, I can pull it up in the Amazon machine learning service console, and I can start looking at it. The first thing I want to do here is I want to look at my target distribution. And I can, right away, I can see that the positive target, or 1, is pretty rare compared to the negative target. This is important to know, and this is important for me to confirm my assumptions. If my assumption before was that my positive and negative instances are about equally present, and I see this picture, either my data is wrong or I need to revisit my assumptions. It's really important to front-load verifying and understanding your data in this manner. I can, of course, look at all my variables by type. I can look at the names of different attributes I have. Here I'm looking at my categorical attributes, and I can, at a glance, see what was the most and least common value for this categorical attribute. How many unique values are there? How well correlated are they to the target? There is a little preview, which I can click on and pull up a histogram of this categorical attribute, which shows me the top variables, and also has a special bar at the right in blue, which shows me all others, the contribution of all others. So right at a glance, I can see this is not a heavy-tailed data set. I can click on any one of these bars and see some sample data records that correspond to these. All of this is built just to enable this effortless experience of swimming through your data, making sure that it looks like you expect it to look like. Anytime it doesn't, you need to either confirm that the data is correct, or you may gain an insight because the data doesn't match your assumptions, and the data is right, it's the assumption that is not correct. And of course, I can do the same thing with other data types. I can pull up a visualization of a numerical variable and change around the histogram to get the right level of granularity. all of this is about just getting insights on your data. The next stage is to train our model. We've created a data source, we've looked at it, we've confirmed that the data is correct. Training the model is, in the service console, is also a wizard. We start off by specifying the name of the data source, which contains our input data. That's the data source we created earlier. And in this way, we have just pulled up all the metadata. We've pulled up where the data is located, how big it is. We've pulled up the schema of the variables within it. And it's really easily accessible just by selecting the data source from the list. Right away, we come to the ML model settings, which is the next step in the wizard. You can see that the model type is pre-filled in here. By looking at the target in our data source, the system already knows this is a regression model. It is used to predict a number directly. I'll talk about different model types in just a second. And here we can choose between a custom or a default flow. With the default flow, I want to emphasize it is not the flow that has absolutely the same defaults for everybody. Default flow really means apply the settings that make sense for my data. So let's take a look at what it looks like. Here I've selected default on the previous slide. I went immediately to the review. At the bottom of the screen, you can see a section that is called recipe. Recipe is our term for the set of transformations that are applied to the data to ensure that this data is optimally represented as input to the learning algorithm. So in this case, I have not specified a recipe, but one was created for me, and I can click on the show button and take a look at what it looks like. A recipe is a very simple language that we've created inside Amazon Machine Learning. It is essentially a JSON string that specifies which transformations apply to which variables or which groups of variables. Amazon Machine Learning implements common machine transformations used in machine learning directly. So all you have to do is specify the name of the transformation, and it is applied at the training stage, and then it is automatically applied in the prediction stage. You never have to worry about synchronizing those two pieces of technology, which I can tell you is a very common source of errors out there. And again, let's take a look at the programmatic way to create this model. It's equally simple. We start off by saying create machine learning model. We specified the ID we want this model to have, the type of this model, and the ID of the data source that will be used to provide the data. So here we are. We have our model, and we should just deploy it to production and go home. Actually, no, we shouldn't. Just having a model doesn't mean it's a good model. It's really important to understand whether the model quality is correct, what the model quality is, and how does it map to business objectives. So we've built a couple of different experiences into Amazon Machine Learning to accomplish just that, to understand the model quality and to actually adjust model interpretation to align more closely with the business goals. I'll show you some screens of what model quality understanding looks like. One important thing to know is Amazon Machine Learning supports several different kinds of machine learning models, or several types of machine learning tasks, I should say. And each task has its own visualization because they are very different in the ways they're interpreted. The first one is what's called binary classification models. And these are some of the most common models you will encounter out there. A binary classification model is one that picks one of two choices. It answers the questions like yes or no. Should I mark this transaction as fraudulent, or should I let it go through? Should I put this email into the spam folder, or is it legitimate? Will this customer click on this item or not, and so on. And so here is our UI for looking at binary model performance. And I'll come back to this UI in just a second because I'll show you how to use it to adjust the model interpretation. A second type of models that Amazon Machine Learning supports is a regression model where we predict a number directly. A business problem might be how many of this type of item do we need to buy in stock? How much will this house sell for? Here you want to predict a number directly, and that's what a regression model does. And we've built this visualization that helps you understand the error distribution around the model so that you can look at it and see whether it aligns with the business requirements. And finally, a third kind of models that is supported in Amazon Machine Learning is a multi-class classification model. Multi-class classification models are used where you need to assign a class or a category to a data record. Maybe I have new items appearing in my catalog. Maybe I have movies, and I want to know which genre the movie belongs to. That is a perfect setup for a multi-class classification problem where each genre is a class, and I feed in the movie metadata and I make a prediction. Is this an action movie? Is it a comedy? Is it a drama? And here's the visualization that we surface up for multi-class classification model. You can see that it's a matrix where we can see the correct predictions on the diagonal and the incorrect predictions, and we can see which classes are often get confused. We can use that now to go back and adjust our data to make a higher quality model. In addition to these visualization, Amazon Machine Learning also surfaces up this easy-to-use indicator of how good is the quality of this model when computed using an industry standard metric for this model type. Each model type has a different metric associated with it, and Amazon Machine Learning gives you an indication of how it scores and how a baseline model would score in the same behavior, in the same situation. So you can see here we have a multi-class classification. If we did the baseline model, which just guesses the most common class indiscriminately, it gets a very low F1 score. This particular model gets a significantly higher F1 score. All right, let's talk about fine-tuning model interpretation, because this is super important. This is a part of what of the skill set that data scientists traditionally brought to the table. Imagine we have a binary classification model here that attempts to answer the question of, is this email spam or not? So of course, we want a model that makes as few mistakes as possible. But beyond that, we can note that different mistakes have different costs. A model like this can make two kinds of mistakes. It can create a false positive, where an email that is legitimate gets marked as spam and put into the spam folder. Or it can create a false negative, where a spam email actually sneaks through and appears in the inbox. When you think about these two mistakes have very different costs. The cost of false negative is, in many cases, annoyance. I look at a spam email, I know it's spam, I delete it. The cost of a false positive is a potentially very important legitimate email going into my spam folder and getting auto-deleted from it after 30 days, and I'll never see it again. This could be disastrous. And so we can actually take this knowledge and use it to inform the interpretation of our machine learning model. In this case, I'm going to grab this slider in the middle and drag it to the right to indicate that I want my false positive rate to be much lower than it is now at 2.4%. And what that does is it affects a special number called the cutoff threshold. Essentially, when a model makes a prediction, it gives us a score between 0 and 1, which is the likelihood of this observation of this data record being positive, in our case, spam. So right now, the threshold is 0.5. You can see it in the upper right corner. By moving it up to 0.81, I've now made a deliberate balance that I want very few false positives. Now I only have 0.5% false positives in my evaluation sample at this threshold. And now I can save this threshold, and it will be applied to the predictions I generate. This is a fantastic way to connect the machine learning models to the business requirements around them. And in just a second, I'll show you how this threshold actually gets used. Because we're about to get to the third stage, which is retrieving predictions. There are two ways to get predictions in Amazon Machine Learning, batch and in real time. Batch predictions are used for asynchronous large volume prediction generation. Whenever you have a data system which itself operates on batches of data, you may have a system that receives new data records. They're imported in a database perhaps on a daily basis, and you want to get predictions for all of these data records at once. Batch predictions interface is the right match for that. The batch prediction interface can be used through either the console or the API. I won't put you through the console wizard because it looks very similar to the wizards we've already seen. Let's look at what it looks like in the API. It's pretty simple. We make a request called create batch prediction. We put in a batch prediction ID. That is the ID of the request that we are about to create. And we can poll on that ID later to see whether the request is complete or not. We put in the ID of the data source that points to the data for which we want to create batch predictions. We put in the ID of the model that is used to generate the batch predictions. And lastly, we enter the URI where we want the predictions to be output. And the output looks like this. The output will be in S3 in one or more CSV files. And it has two columns. There's a column named best answer, and there's a column named score. The score is the actual prediction score for this data record, and these can be merged back with the original data records one by one. And the best answer is what's obtained by comparing that score against the thresholds that we've established earlier. This allows this transfer of knowledge from the person who is building the model to the person who is building the systems that consumes predictions, eliminating any chance for a gap along the way. Next, let's talk about real-time predictions. Real-time predictions is an interface that we provide in Amazon Machine Learning to obtain predictions at low latency synchronously. An API request comes in, and response comes back immediately. And this interface can be used to obtain many predictions at high throughput. It can be requested through the service API. And of course, there is support built into the SDKs, both service and mobile, to request real-time predictions. And it really makes sense for applications that deal with data records one at a time. For example, interactive applications that need to do something for the user right away and need to make a prediction about what piece of content to show to this user, or what to surface to them, or so on. That is a great match to obtain a real-time prediction. So here's what a real-time prediction request looks like. It's very simple. We only specify a model ID. We specify the URI of the endpoint that will be used to query this model for predictions. And the endpoint is something that can be created programmatically and queried with another API. And finally, we pass in a key value map that has our data record. And immediately and synchronously, the prediction comes back. In this case, we have a regression model. It predicts a real number. So the response has an attribute named predicted value. And it also has extra details, like what algorithm was used and what was the predictive model type. All right. I want to finish by talking about some patterns that we have seen for creating smart applications. And I'll focus specifically on patterns for consuming predictions. A common pattern is to work with data that is stored in S3 and to aggregate that data using EMR and then finally generate predictions for it. So an example here might be you instrument data usage or application usage with events. These events go into an S3 bucket. And you want to make predictions as you go along about, for example, when will this user churn? So a common flow for this is to start with raw data in S3, to aggregate, join that data with other data sources you have by running an EMR job, end up with aggregate data again in S3, query for the predictions with the machine learning batch API, which is a great match here because we start with a batch of data and we want to get predictions for every data record in this batch. And then pick up the predictions when they're completed from S3, and then your application can consume these predictions directly. It's a very straightforward data flow. Another data flow is to start not with data in S3, but to start with data in a database or a data warehouse. Here we have structured data in Amazon Redshift. You can query this data directly from Amazon Machine Learning to create a data source and to obtain predictions for this data source using the batch API, which again is the right match here because we have a batch of data records that we want to get predictions all at once. These predictions are output to S3, and now you have a choice. You can import those predictions back into Redshift and merge them with the data that is already there. Or you can pick them up from S3 and consume them in your application directly. The choice is yours. It really depends on what makes most sense. A third pattern, and this is a really simple pattern, it only has one arrow, is using the real-time predictions. The real-time API is great when you have a data record and you want a prediction for it right away. All you have to do is call the API directly. You pass in the data record exactly as you have it, and you get the prediction back right away, and you're able to consume it. So in this case, maybe you have a mobile application that needs to decide which offer to show to the customer next. It can query the server directly with the data record, which contains the current state and maybe the list of current offers, and it will return the prediction will have the information the application needs to actually implement this. And finally, the data flows that I'll close with, it's an interesting one. It is taking an existing application and augmenting it with predictions. So imagine we have an application that writes rows to DynamoDB, and this application exists today. And we want to augment these rows with predictions. What we can do is not change the application at all, let it write to Dynamo. We can use AWS Lambda to kick off an event when a new row is written, have that event generate a prediction for this row, and then write this prediction back into DynamoDB. So now the data is augmented. You can imagine a use case where, for example, I have a mobile application that sends an event every time a user performs an action, and the DynamoDB rows are augmented with a prediction of how long will be before this user session is over. And this can now be consumed by this same application or by a different application. The data is all in one place. So at this, I will finish up. Thank you very much for being here. I really appreciate your time. So, thank you. Please rate the session with a mobile application if you have it installed, and I would be happy to take questions. Do we have microphones for questions there? Hey, hang on just a second. We'll get the microphones figured out here.
Hi, Alex. What kind of supervised learning algorithms are available?
So as I mentioned, Amazon Machine Learning, I'll answer the question a little indirectly. Amazon Machine Learning supports 3 types of machine learning tasks, which is binary classification, MultiClass classification, and regression. The algorithm we use, or the algorithms we use to do this are all variants of linear models. So they're generalized linear models. So it's logistic regression for binary classification and linear regression for numerical regression tasks.
And are you planning to add more advanced algorithms like, I don't know?
We definitely have more algorithm support in our roadmap. We will listen to our customers and build what is needed. Absolutely.
Thank you.
I think we have a question over here in front.
Hi, can you give examples of Amazon itself using this, like for its recommendation engine and shopping?
Well, one example I can talk about is the example of there is a team within Amazon that is using some of the same technologies that Amazon Machine Learning is based on to make decisions about which products it makes most sense to implement a type of sustainable packaging for. And there are many other examples like this. But the important thing here is that this technology has been a real enabler for teams inside Amazon and for customers in our private beta program to build the applications that they have not been able to build before for various reasons that I've talked about. Questions back?
So Spark has launched a machine learning library, and Spark can run on EMR. Can you compare and contrast how using Amazon's machine learning library might compare to using Spark's? What are some differences there?
The important thing, I think the important thing here is the way we have built Amazon Machine Learning is that we looked at what mattered the most to our customers, and that was ease of use and robustness. And we've built the service to really speak to these ease of use, robustness, and operationalization. We're always looking at technology out there to see which of it makes sense for us to implement as a part of Amazon Machine Learning. It will definitely drive our roadmap. Go ahead.
I think this is very cool to make machine learning available to just about anybody. But if I were a hardcore data scientist, I would probably say this. I would say, well, A real system like this has lots of algorithm choices and lots of tools for shaping the data and controlling the data. And this is so simple. 3 algorithms, you choose them, no tools for modifying the data. They would say, I would suspect, that this is so simple that it won't produce good results compared to using a specialist who knows the algorithms can do a lot more. What do you think?
Well, I'll say this. What our experience has been is that many machine learning applications out there do not exist because there are not enough people to create them. And what we've really tried to do with Amazon Machine Learning is to enable and empower a large number of people to build machine learning applications. Another experience I'll relate is that it's again been our experience and our customers have told us the quality of machine learning applications comes first and foremost from data. It's all about having good data. It's all about having enough data. And it's all about being able to leverage that data in useful ways. And so with Amazon Machine Learning, we're enabling our customers to use the data they have to build applications that they were not able to build before because they didn't have the resources or they didn't have the right technology basis, they didn't have the right things in place. It's been our experience that this technology opens up the door to more and more machine learning applications to be built.
So the models are good enough, even though they're not quite as good, perhaps as those built by hardcore data scientists. Your experience has been they're good enough to solve the problem.
I won't speculate on what the line is between a good model and a good enough model. I will say that we have seen case after case of customers, both inside Amazon and our private beta customers, being successful by using Amazon Machine Learning.
I have 2 brief questions, if I may.
Yes, please.
The first is there going to be a way to input data from an arbitrary MySQL connection, or will we have to dump our data into an Amazon service first? And then my second question is, are there plans on having some way of introspecting a particular prediction and seeing how the model arrived at that prediction? Those are my questions.
Right, makes sense. The answer to the first question is, today Amazon Machine Learning works on data that is already in the AWS cloud. So it will connect to a MySQL instance in RDS directly, or it will read data from S3. So S3 is often the universal connector between different data sources. It might be a very reasonable way. With respect to the second question, we will always look at prioritizing our roadmap based on the customer impact. We've certainly, this is a request we've heard, and it's in our roadmap.
The service is really cool. I like the interface. My question is regarding the cleaning of the data.
Mm-hmm.
So when I have worked previously on machine learning, most of my time was spent in cleaning up the data and getting it in the format which actually works. And one example will be like product information, which is mostly text. Can you give a little bit on insight, like how the user should be providing that kind of a data for prediction models?
Yes, and your experience is certainly an experience that we have that is mirrored by our internal and data experience as well. So much of building a machine learning system, a machine learning based application is about data cleaning, getting the data, cleaning it, and putting it into the right format. There are a few things that I want to mention. One is that by supporting CSV files in S3, we again are able to support this, one of the most common carriers of data imaginable. And by shipping with a set of data transformations right in the product, we enable you to do interesting, powerful things with that data. So let's take the example of free text data. Maybe we have emails and we want to categorize these emails as, for the purpose of routing them to the right customer service representative. It's a very common machine learning use case. You can start by simply having a CSV file with 2 columns. One column is the label, and the second column is the entirety of that email you'll have to process to remove the new lines. And then you can apply the built-in data transformers that are a part of Amazon Machine Learning on top of it. So you can say, take this field, I will call it email body, lowercase it, generate trigrams from it, and then feeds that into the machine learning system. This has become as simple as editing this our recipe JSON string. You don't have to deal so much, you have to spend so much effort on featurizing your data before you can feed it into the machine learning system. I also want to point something out, and this is important. We've made Amazon machine learning, we've deliberately made the choice to make it robust to occasional data problems. Having some observations, some data records that are wrong is not going to derail your model. Having too many of them will, but having a few of them be wrong is not going to be a big issue. Having some data records that are malformed is not going to abort the model training request. It's going to proceed as needed. We've made it resilient to these common types of problems because we want our customers to be successful, and getting every single data record just perfectly is not a recipe to quick success, certainly.
Hi,
Hello.
very nice presentation. Thank you.
Thank you.
I have 3 questions. The first one is very straightforward. Is this built, implemented at Amazon in-house, the algorithm, or you use the open source implementations packages? And my second question is, I wonder if you can comment on the performance, and especially in terms of the size of the data sets that you guys have tested, and how fast it can run, and the prediction accuracy. And the third one is about the data types manipulation, especially regarding how well it can manage, say, categorical variables and the missing values. Thank you.
Yeah, so let's take those from the top. The first question was, sorry, I'm totally drawing a blank here. The first question was, I'm so focused on the second and the third, I've lost my, open source, right. The algorithms that we use, in Amazon machine learning today, is our own internal implementation of an industry standard generalized linear models algorithm. And we've chosen our own implementation to make sure it can achieve the right performance and robustness characteristics. The second question was on the performance of the system. We support input data sets for training up to 100 gigabytes large. The time it takes for a data set for a model to be trained, or for predictions to be generated, or for data statistics to be computed, it really varies. It varies on the size of the input data, certainly. It varies on the number of variables and their types. It varies based on the types of data transformations that you have chosen to apply to these variables. So it's hard to give a specific answers there, but we've certainly made it performant enough to be used internally inside Amazon for some very important applications. And our private beta customers have also used this with great success. And then the third question, I believe, was about predictive accuracy. Is that right? Predictive accuracy is all about the data. It's garbage in, garbage out, or more politely, gold in, gold out. Great data leads to great machine learning models. It's very difficult to generalize, what the predictive performance will be on one data set or another. In general, again, the types of models we use are an industry standard. They're used by some of the most sophisticated machine learning applications you see out there use the same kinds of models. So the potential is there, but that potential is not realized without having great data.
Hi. Let's say we've created our model and trained it and tested it and finished it, but I want to deploy it outside of Amazon. Can I export it?
No. The models that you build with Amazon machine learning are deployable to the Amazon machine learning fleet, and so you can query them using batches or real-time API in the AWS cloud. We're at about 1 minute, so we have time for probably one more question, and the microphone is coming right behind you.
So how can I reasonably estimate how much I will pay? Say I send 10 gigabytes of data for training.
For training, it's very simple. The actual amount you'll pay is based on the number of compute hours that are used. You can draw some very reasonable inferences about for your particular data set, how many gigabytes per hour can be done by doing a little experiment. Again, depending on how much data you put in and how complex the data is, how dense it is, how many feature transformations need to be applied to it, the result will be different. But it is trivially benchmarkable, and you can have very, very good expectation. All right, we're at time, so thank you very much again for being here. I really appreciate your time.